Okay, look at these two drawings. At first, they look almost identical, right? Both show two walkways hanging inside a hotel. But in the first drawing, each walkway hangs from the roof. In the second, the lower walkway hangs from the upper one. And yeah, that tiny change made one connection carry twice as much weight. But here is the scary part. Nobody properly checked it. On July 17th, 1981, that connection failed above a crowded hotel party. Two concrete walkways fell into the atrium. It became one of the deadliest structural failures in American history. So, how could such a small change pass through designers, builders, and inspectors without anyone stopping it? This is Failure Atlas, and this is the Hyatt Regency Walkway collapse. The Hyatt Regency was a new hotel in Kansas City, Missouri. Its main attraction was a huge open atrium. 3 glass walkways crossed high above the lobby. The second and fourth were stuck above each other. The third sat off to one side. Honestly, the whole place looked beautiful, yeah. But on Friday evening, the hotel held a popular dance event. By 7 o'clock, between 1,500 and 2,000 people were inside the atrium. People were dancing, talking, and just enjoying the evening, Others stood on the walkways and watched from above. At 7:04, the band returned from a break. It began playing for a dance contest. Then, 1 minute later, just 1 minute later, there was a loud crack. The 4th floor walkway dropped onto the 2nd floor walkway below it. Then both fell into the crowd. No real warning, no time to move. The collapse took only seconds. And the answer to why it happened begins with one metal nut. Each walkway was held up by long steel rods. The rods came down from the roof. They passed through hollow steel beams under each walkway. A washer and a nut sat beneath each beam, so the rod pulled upward while the nut held the beam in place. Okay, imagine 2 climbers hanging from the same rope. One is above the other. Both climbers are holding the rope themselves, so each person carries their own weight through the rope. The lower climber is not hanging from the person above. The original walkway design worked in a similar way. One long rod passed through the upper walkway and continued down to the lower one. The upper connection carried only the upper walkway. The lower walkway sent its weight farther down the rod. Pretty simple, right? That was the plan shown on the approved drawings. But the steel fabricator found the long rod difficult to build, so the connection was changed. Now, instead of one long rod, there would be 2 shorter rods. One connected the roof to the upper walkway. The other hung the lower walkway from the upper walkway. At first, that probably looked like the same design, just drawn in a different way. But the path of the weight had completely changed. Now, let's go back to those 2 climbers. Imagine the lower climber lets go of the rope. Instead, he grabs the legs of the person above him. Suddenly, the upper climber must hold the weight of 2 people. And yeah, that is exactly what happened here. The upper connection now carried both walkways. Its load had doubled. Physics doesn't care that true drawings looks almost the same. Now, this is the moment when someone should have stopped everything. A change this important needed a new calculation, but this is where things became messy. The fabricator asked about the new rod arrangement by telephone. The project engineer gave verbal approval. He expected a formal written request later. That request never arrived. Then, some of the shop drawing work went to an outside detailer. The detailer believed the connection had already been designed, so he didn't calculate it. Back at the engineering office, a technician reviewed the drawings, but the critical connection was not properly checked. The engineer performed only spot checks. Then he placed his professional seal on the documents. I mean, everyone touched the drawing, but nobody followed the new load all the way through the connection. The drawing received approval. The connection never received the calculation it needed. At the party, the people on the walkways finally added more weight than the connection could take. And here is the strange part. The steel rod itself did not simply snap. Instead, the nut and the washer pushed into the thin bottom of the box beam. The steel around them bent. Then it tore open. Think of pulling a button through thin cardboard. The button may stay whole, but the material around it rips apart. Once that connection failed, one end of the fourth floor walkway gave way. It struck the second floor walkway beneath it. Then gravity did the rest. Both walkways crashed to the floor. The first emergency call reached the fire department at 7:08. Rescuers faced enormous pieces of steel and concrete. People were trapped underneath. By the end of the disaster, 114 people had died. More than 200 were injured. Just imagine that. A busy Friday evening changed forever in a few seconds. Investigators studied the broken steel. They tested full-size copies of the connections. They also examined video recorded just before the collapse. They estimated that about 63 people were standing on the two walkways. This was not some impossible crowd that no building could be expected to hold. The connection failed far below the strength required by the building code. With the changed rod design, it could carry only about 31% of the required load. 31%! Let's think about it for a second. Even the original design would have reached only about 60%. So the change did not turn a safe connection into a weak one. It took a connection that was already too weak and made the problem much worse. And no, the disaster was not caused by people dancing too hard. Those people trusted the building to hold them. The walkways had been dangerously weak from the day they were built. After the investigation, Missouri revoked the professional licenses of 2 engineers involved in the project. Engineering rules also became clearer. The engineer who seals the structural design is responsible for its safety. That includes important connections shown in shop drawings. Now, it would be easy to search for one villain here, but honestly, this was a whole chain of small decisions. Each person saw only one piece of the project. The danger lived between those pieces. A design change is not just paperwork. It can quietly rewrite how every force moves through a structure. And if nobody checks that new path from beginning to end, well, a tiny drawing change can become a real disaster. You know, this is the part that really stays with me. The two drawings looked almost the same. There was no strange new material, no impossible equation, or no giant warning written across the page. One long rod had simply become 2 shorter ones. But that small change moved the weight to a completely different place, and somehow nobody caught it. The danger did not stay hidden because the maths was impossible. It stayed hidden because the people around the drawing never connected all the clues. And honestly, that is a pretty frightening thought. So, if you enjoy simple stories about complicated failures, consider subscribing to Failure Atlas and tell me in the comments what failure should we investigate next.